It says we're recording. So, oh, does it say? Oh, we've got 12 in the meeting. That includes me, so 11. So, all right. I never noticed that before. I guess I should look closer. Okay, so we're going to start on polar coordinates. Whoops, that's not the right thing. I thought I had that open. Here we go. Okay, so this is our last new section. If we can finish, if we go into tomorrow, well, yeah. So let me just mention this week really quick. So as far as this week goes, we're going to cover 6.5 today. If we don't finish it today, we'll finish it tomorrow. And then we'll have a review tomorrow, a review Wednesday, and then the final exam's Thursday. I'm going to make it a little bit longer than a test. I'm going to give you the full 2 hours. By the way, let me just throw this out here. It seems like you guys said test number 1 was a little bit long, but test numbers 2 and 3 have been okay, right? Okay, so it's probably going to be probably 15 problems, I think. And then hopefully that'll be good. So anyway, all right, so here, let me close that. All right, so we're going to do the introduction to polar coordinates. We're jumping all the way up to 6.5. Okay, so polar coordinates are very different because, in fact, a lot of times we'll use a graph similar to this. So the idea here is, rather than pick coordinates, we can specify a point by the length of the ray and the angle. So the point is the length of the ray r and the angle theta. So we're always measuring it. You can think of this as the x-axis, but we're going to call it the polar axis. And so this point here would be the radius r, or the ray r, and then your angle theta. So points are not uniquely identified. For example, 4 negative 7 pi 6 is the same as negative 4 pi 6, or you could say 4 and 5 pi 6. So that's 3 ways to describe the same point. Okay, so the idea, the polar equations of a line, so we can define lines different ways. The graph theta equals A is a line through the pole, so we call the center the pole, at the angle alpha from the polar axis. I've got some more things here in a minute. The graph R equals sine of A. You know what? I'm going to change my notes around because I put this really in the wrong spot. Right here. Okay. The graph r sine theta equals A is a horizontal line passing through the point. And so I've got that here. You've got your horizontal line here. And your graph r cosine A is a vertical line passing through the point, okay? So there's 3 different ways you can draw a line. You can just say that theta equals some angle alpha, and here's a straight line. Or you could do a straight line as r equals sine theta, r sine theta equals alpha, and that will be this. And then you can do r cosine theta equals A. That would also be a straight line with polar coordinates. So, so that works out pretty well there. Okay, now let's talk a little bit about circles. I think I'm going to move that up here because this is going to mess me up. I knew that was going to happen. Okay, I think this is better. Okay, so we don't have, unfortunately, any graph paper that looks like polar paper. You can actually buy it, but this would be an example of the graph paper you can buy to do that. But we've also got some various points, 3 pi thirds, so you're just going up 1, 2, 3 units, and you're at pi thirds. We talked a little bit about this, 4, -7 pi 6. Once again, that's not a unique coordinate. Anyway, so the first number is your length of your radius. The second number is your angle. Oh, now that doesn't fit on the same page here. Let me make this just a little bit smaller. Hopefully that'll fit on the page. There we go. I can make it a little bit bigger here. All right. R equals A will be a circle of radius, whatever your length A is. This is an example of R equals 2. So you can see that in polar coordinates, a circle is a much simpler equation here. Theta equals pi 6. We mentioned that's a straight line as well. Sorry. There we go. Okay, let's talk a little bit about symmetry, okay? Now, if you can substitute negative theta for theta, then you're going to have symmetry with respect to your polar axis here. So this would be an example of symmetry with respect to the polar axis. You can see that r theta and r minus theta, those are symmetric about the polar axis, okay? You can also substitute pi minus theta for theta and negative r for r. That would also be an example of symmetry with respect to the line theta equals 0. Now, and I've got some graphs here I'll show you in just a minute. If you can substitute theta minus pi for theta, that can show symmetry with respect to pi halves. Remember this here. So the way this works is this is 0, this is pi halves, this is pi, this is 3 pi halves. So if you can substitute pi minus theta for theta, that can show symmetry to the line theta equals pi halves. If you can substitute negative theta for theta and negative r for r, that also shows symmetry to the line theta equals pi halves. If you can substitute negative r for r, then that shows symmetry to the pole. And remember, the pole you can think of as the center. Normal in rectangular coordinates, we'd call that the center. And if you can substitute pi plus theta for theta, that also shows symmetry to the pole. So a test for symmetry may fail one test, but not another. So for example, sine of 2 times negative theta equals the negative sine of 2 theta. So so you can think of this as your negative r. That does not equal your r in the original thing. However, you can if we substitute theta minus pi for theta, then we can show that that is, so in this case, that would be symmetric to the theta equals 0 line. So some examples here. This would be an example of r theta and r theta minus pi. These two lines would be symmetric about your pi halves line. And so symmetry with respect to the pole, if I have r theta and minus r theta, those would be, or rather r and theta plus pi, this line here would be symmetric to this line here. And so that would be an example of symmetry with respect to the pole. So any questions you guys have on that so far? Okay. Now, you'll find here that in some cases things are easier and in some cases they're a little bit harder. So sketch the graph of r equals 4 cosine theta. Now, the nice thing about that, in polar coordinates, this becomes simply a circle, okay? So the idea here is there are different ways you can get a circle. R equals a cosine theta is a circle symmetric to theta equals 0 line. R equals a sine theta is a circle symmetric to theta equals pi half. So r sine theta would be a circle of radius 2, well, just like that, okay? Now, the one thing that I do want to focus on, remember, this is r equals a cosine theta, and it's a circle. Remember, when we went back here, the r and the a were flipped right here. R sine theta equals a is a straight line, okay? So I know that these look very similar, but remember, so r equals sine of theta or cosine of theta is going to be a radius of length a. And if we put this on the other, if we put the cosine or the sine on the other side of the equals, it's now a straight line, okay? Some examples of these are, so that r equals a, this is going to be a circle of radius a. R equals a cosine theta is going to be a circle with the polar axis here. And r equals a cosine theta is also going to be a circle, but rather than being symmetric about the polar axis, we're going to be symmetric about pi halves. Okay? All right. So in polar coordinates, there are other shapes that we should know. Okay, so we've gone over straight lines and we've gone over circles. Now, these are some other shapes that we're going to need to know. We need to know a limicon. In fact, I'm going to do this before I go over the definitions. So we've got a convex limicon, okay? You can see that this looks like a circle, okay? It has no dimple. A limicon with a dimple is going to be shaped like this. A cardioid is what we're going to call a heart-shaped limicon. It looks a little bit like a heart, so that's where we get cardioid. And then we get a limicon with an inner loop, okay? So these are your four types of limicons. You get a limicon with a dimple, a heart-shaped limicon, and a limicon with an inner loop, okay? Now, so let's talk a little bit about these. The graph of the equation r equals a plus b cosine theta is a limicon that is symmetric with respect to the line theta equals 0. So you can see all three of these, well, really all four of them, are limicons that are symmetric to the polar axis right here, okay? The equation r equals a plus sine theta is a limicon that is symmetric with respect to theta equals pi halves. So the only difference between is we've changed sine and cosine. So basically all of these we could flip it 90 degrees and it would be a limicon with respect to the pi halves line. In the special case where the absolute value of a equals the absolute value of b, this graph is called a cardioid, okay? Now, when we talk about the a and the b here, okay, if the absolute value of a over b is greater than 2, that's when you have the convex limicon, which looks a lot like a circle that's off center this time, or off pole, I guess I should say. If the absolute value of your a over b is between 1 and 2, you're going to have a dimple here. If the a over b, the absolute value of a over b equals 1, then the dimple goes through the pole. And if A over B, absolute value of A over B is less than 1, you're going to have the inner loop with your dimple, I guess. Okay. Now.
So I have a question real quick.
Okay, go ahead.
So the difference between the limicon with the dimple and then the heart-shaped one is the heart-shaped one is going to go with the 0, 0, like in the center?
Correct.
Is that right? Okay. Thanks.
Yeah. Now, I will ask you a question. I know I'm much older than all of you people, but when I was a kid, we had the little spirograph, those little circles, and you could draw all of these shapes. Did you guys play with those when you were kids? I don't think my kids have. I think they're deprived. I might have to get them this. But all of those shapes are limicons and cardioids. They're based on polar coordinates. And so, so that was a fun toy as a kid. All right. So if we sketch the graph of r equals 2 minus 2 sine theta. Okay, so the idea here is hopefully you can recognize this as a, this is going to be a cardioid, right? Okay. Now, the idea here, so I want you to be able to just look at this and go, I know that's going to be a cardioid. Now, the key points, there's going to be 4 key points that we're going to want to graph on this. First of all, you should just look at this and know this is a cardioid, okay? So when theta equals 0, so sine of 0 is 0, so 2 minus 0 is 2, okay? And so the idea here is I'm going to go 2 units to the right, and I've got this point right here, okay? When theta equals pi halves, sine of pi halves is 1. 1 times 2 is 2. 2 minus 2 is 0, so that puts me right in the pole, okay? When theta equals pi, sine of pi is -1. -1 times -2 is +2. 2 plus 2 is 4. And so it's funny because we're saying 4, but the idea here is, actually, I said that wrong. I did the 3 pi halves. Sine of 3 pi halves is 1, -1. -1 times -2 is +2. And so at 3 pi halves, we're going to go out 4 units here. And then sine of pi is 0, so 2 minus, I don't think that should be -2. It looks like -2, but we're going out pi units and we're going out 2. So the idea, the 4 points that you should really make sure that you know are this first one at 2, 0, 2, and 3 pi halves, okay? And then you can draw your limicon right there. Does that make sense? Okay. All right, now we're going to do polar coordinates of rose curves, okay? So the graph of the equation r equals a cosine n theta and r equals a sine n theta are rose curves, okay? They look like this. When n, the number before your theta, is an even number, the number of petals is 2n. When n is an odd number, the number of petals is n. So some examples here, if n is 4, then you're going to have 8 petals, okay? And so the idea is if you're drawing these, I think you're going to draw them like this. This is where the spirograph comes in because it's pretty cool. Anyway, if n is odd, like 5, then you're just going to have 5 petals. So you're going to go something like this, and that will be your rose petals. So, quick question here. Let's pick on Cameron Ravert. How many rose petals are in the graph of 4 cosine 3 theta?
Wouldn't it be 6? Because 2 times 3 is 6.
No, because 3 is an odd number.
Oh, yeah. So it'd be 3 then.
So it would be 3. Okay. Josue, how many petals am I going to have in r equals 5 sine 2 theta?
I think it's 2.
No, 2 is an even number. So you're going to have to double it. So that would be 4.
Oh, 4. Oh, okay.
Boy, struck out on that one. All right, so 3 is an odd number, so you're going to have 3. 2 is an even number, so you're going to have 4. Okay? All right, so if we were to graph r equals 2 sine 3 theta, you know you're going to have 3 petals. Now, another thing to think about here, I know I've got a big, oh, actually that chart's in the wrong way. Okay. So the idea here is you're going to go every 120 degrees, okay, because you've got 3. So, so you can go, you'd probably start here, 1, 2, and 3, okay. So when you're picking your theta, it's probably easiest to pick something so that it's easy. So you're going to pick 5 pi 6th because 3 goes into 6 twice, and so that will be the same as pi halves, and then you can do that way. So this is the table that they used here for this graph. Okay, so when theta is 0, you've got 0. When you have pi 6, you're going to have your r as 2. When you have pi thirds, you're going to be back to 0. And anyway, so you can use this table. I wonder if I could put that on there. Maybe I'll just make that a little bit smaller. So you can use this to kind of plot points here to get these 3 petals. So does that make sense? I'll make that a little bit bigger. Okay. All right, so now, because we're probably more familiar with rectangular coordinates, we're going to talk about how to convert between rectangular and polar coordinates. So given the point r theta in the polar coordinate system, the transformation equations change from polar to rectangular coordinates. X is going to equal r cosine theta, and y is going to equal r sine theta. So that's probably very familiar to you guys. Given the point xy in the rectangular coordinate system, the transformation to change from rectangular to coordinates r is so this is just Pythagorean theorem, r is square root of x squared plus y squared. Tangent of theta equals y over x, and of course x cannot equal 0 or you're in trouble. So r has to be greater than or equal to 0. Theta has to be greater than or equal to 0, or between 0 and 2 pi. And theta is chosen so that the point is in the appropriate quadrant. If x equals 0, then theta equals pi halves or 3 pi halves. Okay, so we'll do a quick example here. Convert 6, 3 pi fourths to rectangular coordinates. We'll just use this equation here. X equals 6 cosine 3 pi fourths, and that will be, so your x coordinate is going to be the negative 3 square roots of 2. Y is going to be 6 sine 3 pi over 4, which is going to be 3 square roots of 2. So your coordinate, so converting 6 3 pi fourths works out to be negative 3 square roots of 2 and 3 square roots of 2. Okay, so let's have you guys convert negative 4, 30 degrees to rectangular coordinates. So let's, what is this? Let's go to Graham. Graham, can you do that?
Which one did you want me to do? Oh, that one right there.
converting 4 30 degrees to rectangular coordinate, -4 30 degrees, okay? So how would you do that?
So you would do, let's see, x equals -4 cosine 30. And that would give us our x value. And then y is the same, is it the same thing? -4 sine 30.
Okay. And the cosine of 30 degrees is?
√3/2.
And we're going to multiply that times -4. Okay, so your x-coordinate's -4, square roots of 3/2, and your sine of 30 degrees is?
It'd be -4 times 1/2.
1/2, which would be simply -2, right?
Yep.
So putting this in xy form, we're going to have what?
It would be -2 square root of 3, comma, -2.
You meant -4 squared. Oh, no, you're right. -2 squared root of 3, comma, -2. Okay. So that was nice and easy. And I've got a nice thing there, so it looks better. Okay, what about if we're going to convert it the other way? Remember that. So whose turn is it now? Chris Hardwick. Can you convert this for me?
Yeah, so let's see. So you just do square root of 2 squared plus 2 square root 3 squared. Or would it be 2 squared square root 3 squared?
Yeah, let's see if we can just do this in our head. So 2 squared is 4. Square root of 3 squared is 3. So 4 times 3 is?
Is 12.
12. And 2 squared is 4. So I got the square root of 16.
4.
So r equals 4.
R equals 4.
R equals 4. Okay.
And then after that, you do the tangent of, what was it, y over x. So it would be tangent of -2 square root 3 over -2.
Okay, so the -2's will cancel. So this is just going to be the square root of 3. And what's the inverse tangent of the square root of 3?
Inverse tangent of square root 3. Let's see if I could remember that. I can't remember right now.
Who remembers?
Is it square root of 3 over 3?
No, it's just the plain old square root of 3.
But with the inverse, wouldn't it be 1 over 3 to make it square root of 3 over 3?
No,
Or
I've
no?
got to come up with an angle like 45 degrees or something like that.
Oh,
30,
gotcha.
45, 60. It's one of those.
Is it 30 degrees?
Was that a Jeopardy question?
Yes, it was. I'm saying 30 degrees.
How about 4 pi thirds? Okay. So part of the problem here is, let's think about this. We probably should have drawn our graph, right? Where's my paint? Okay. I'm going to try to draw these. In fact, maybe I'll add this to my notes here. Ooh, well, maybe that's okay. Okay, now I don't like that. No, here we go. So if I draw my graph here, We're in rectangular coordinates, so we're normal, right? And we're at -2 and then -2 squared roots of 3. So we're definitely in this quadrant here. We're in quadrant 3, right? And so basically this graph here, this here is pi thirds. Pi thirds. And so because we're in quadrant 3, therefore we're using 4 pi thirds as our thing here. Okay? Does that make sense?
Yep.
Maybe I'll add this. So 4 pi thirds. Actually, here, we'll do it that way. Wrap text. Whoops, whatever I did, I didn't mean to do that. Okay. All right. Okay. It's a little big. Okay, so write r squared cosine 2 theta equals 3 in rectangular form. Actually, this one's a little trickier. So remember from our identities that we've already forgotten, cosine of 2 theta equals 1 minus 2 sine squared of theta. So therefore, I can rewrite cosine of 2 theta as 1 minus 2 sine squared of theta. So we've got r squared minus 2r squared sine squared theta equals 3. And so we can rewrite this as r squared minus 2 times r sine theta quantity squared equals 3. And we remember that r squared equals x squared plus y squared. So I can substitute this in for here. And r sine theta is just y. So now I've converted this to x squared plus y squared minus 2y squared equals 3. And therefore x squared minus y squared equals 3. So that was a fun one, okay? This one we get to remember our identities, which we've forgotten, especially that one. Okay. All right, let's write 8 cosine theta in rectangular form. So if I do this, I've got r equals 8 cosine theta. I can multiply both sides by r to get r squared equals 8r cosine theta. We remember that r squared equals x squared plus y squared. So now I can substitute this right here. And we remember that the cosine of theta is x over r. And so now this r cancels that r. And I've got x squared plus y squared equals 8x. So now I can set the whole thing equal to 0. X squared minus 8x plus y squared equals 0. Now I can complete the square on the x term here, okay? And so I'm going to take half of 8 and I'm going to add 4 squared to both sides. So this becomes x minus 4 squared plus y squared equals 16. And hopefully by now you recognize that this is a circle of radius 4 with your center at 4, 0. Okay. Carl, I thought we were going to go long today. We're going to get done early. Okay, so finally, write r equals 8 cosine theta in rectangular form. Okay. So This looks like what I just did. No, I guess it's not. Okay. So we can remember that x equals r cosine theta and y equals r sine theta. I think I've messed this up. This isn't the same thing. No, this is supposed to be this. We're going to do that in, I think this is what happened in polar form. Okay, so write x squared plus y squared minus 2x equals 3 in polar form. So we remember that x equals r cosine theta and y equals r sine theta. So this is going to be r cosine theta squared plus r sine theta squared minus 2r cosine theta equals 3, okay? So now if I factor out the r squared out of both of these terms here, I'm going to end up with r squared times cosine squared plus sine squared. That's going to be 1. And so this is going to simply be r squared minus 2r cosine theta equals 3. Okay? So I've converted this from rectangular form to polar form. And in the words of Forrest Gump, that's all I have to say about that. So I thought we were going to take a long time today. We got done really early. So do you guys have any questions for me?
So for those last couple ones we just did, is most of that going to be just remembering old identities and needing to apply those? Okay.
Yes.
To do some review then.
So yes, so this is going to be a definite review now. So tomorrow we've got the quiz 6.5. This is your last quiz. And then last quiz, last homework. You are definitely going to want to review some of those old identities. Tomorrow, or what I think would be best, since you've just had your test so we've had 3 tests, right? So, and you guys seemed like you learned that pretty well. So tomorrow, I've already posted the review for test number 1. I posted that, weeks ago. So let's make tomorrow our lecture. So homework and quiz is due tomorrow, so we'll do that first. Then the rest of class is going to be review number 1. Thursday will be review number 2, and then I'm just going to hope that you can remember review number 3 because you just took that test a couple days ago. So Thursday I'm going to give you 2 hours for the test, and is there anything else? So yeah, so basically the reviews are already posted. So any questions for me?
I do have one question.
Go ahead.
Whenever we take the final, would it be possible if you could drop 2 of our lowest scores?
No, because that's not against department policy.
Oh, bummer. I had to ask. So
yeah. So and I will tell you something, Texas. Back when I used to work at Salt Lake Community College, and they used to, for Math 1050, I know, which is a little different than this, they would give you like 20 questions that were multiple choice, and then you had to pick 5 of the last 10 questions, and you could pick any 5 that you wanted to do, which sounds really fun, but the accreditation committee came and they said, well, that's not fair because, Nicole, she did the easiest 5 problems and Texas did the hardest 5 problems. And so they weren't being tested the same. And so that's actually against accreditation standards. So, so that's a bummer.
sense.
Yeah. It's fun when you get to choose your questions, but they say no, that's not a good idea. So
Okay.
So let's see. By the way, I updated your homework grades. Those are updated. I've been working on attendance. I've gotten part way through that, so I'll try to get those done today. Although no guarantees. It depends on how busy I am. So, any other questions you guys have? Okay. Well, do you feel excited that you've learned the last new thing you're going to learn in this class?
I do.
Nicole looks just giddy. All right. Well, I'm going to let you guys go. I'll make my quiz. And so just remember, homework and quiz due tomorrow. Review the first exam review. That will be what we will focus on tomorrow. And we'll see you all tomorrow.
See ya.
Have a good one.
And if anyone